Good afternoon, everyone. Um, my name is Joe Kamdani. I'm the CTO and co-founder of Kickfire. Probably you've heard the company from the keynote speak a couple of days back. And it is my pleasure to share with you here some of the kind of the nuts and bolts inside Kickfire. Since this is a technical presentation, my slides are mostly, talking about technical stuff, and feel free to stop me or ask me a question in the middle. The focus of the talk is not to present anything, but rather to share with you what hardware and software techniques we've done inside Kickfire analytic appliance to reduce I/O bottlenecks, in particular in data warehouse applications, which tend to have complex queries as well as a very large data set. So just to get the sense of the audience here that I'm talking to, if you don't mind, if you could raise your hand if you are currently deploying data warehouse or maintaining a data warehouse application. Very good. Okay. Looks like we have a good crowd. How many of you, or if you could raise your hand, thinking of deploying data warehouse with MySQL? Okay, that's a good crowd also. All right. So with that, let me show the brief outline of my talk. First, I will give an introduction of Kickfire, and some of the vision of Kickfire I will share with you, and also what are the other technology besides reducing I/O. I will touch base on that, in particular how with our SQL chip we changed the paradigm of database computing. Then we'll go over the crux of the presentation, which showing you, based on our experience, what are the I/O pain points in data warehouse or analytic applications, and also in particular in talking to many MySQL customers that are deploying or trying to deploy data warehousing, what are those I/O pain points. We were here last year introducing the company for the first time out of stealth mode, and since then, over a year, we have talked to many MySQL customers trying to deploy data warehouse, which is somewhat different with the traditional data warehouse, especially those that deploy with commercial databases like Oracle, DB2, or Microsoft SQL Server. And then we'll get into the architecture features that leading to this efficient I/O. As I'll show you shortly here, that our solution is in small 2 rack unit and 3 rack unit, depends on the model, that can fit in a standard rackable space. So, but yet the performance, sometimes it can beat the whole cabinet of hardware complex. Okay, and I'll also briefly mention about the TPCH benchmark that we've done and the experience that we've gone through. This is, again, if you're not familiar with TPCH, is the widely accepted industry benchmark for data warehousing, and this is where you are being measured with other commercial databases, and the hardware vendors also that is running these commercial databases. Okay. So when we started the company, we have this simple vision, which is we'd like to provide high performance database appliance for data warehousing or analytics application. We're not trying to be everywhere, trying to be the solution provider for OLTP, for example, which is where MySQL is very popular also. But what we see here as, where MySQL is very popular, but yet somewhat getting resistance when trying to be deployed as a data warehouse solution is the performance. There's so much invention being done in the commercial databases, those big three, over a decade with their parallel query and so on. And as you probably aware, that MySQL is not, it's not running a single query or processing that single SQL statement in parallel, leveraging the multi-core processors, for example, things like that. So that's where it's needed, parallel query. I'm not talking about many queries in a throughput environment. I'm talking about a single complex query, how we break it down and run it with multiple processing resources. So, but one thing that is along the line with the open source spirit is that it has to be low cost. In fact, our goal is to be the lowest cost solution, and that is one metric that is very important. And TPCH is measuring also price performance, and we're number one in the TPCH benchmark on 100 gig and 300 gig category. So, in a simple illustration, what we're trying to do is, what if we could get the performance of this, 3-rack wide cabinet, hardware system running commercial database. And this is a real picture that I captured from one of the TPCH report. One of the hardware vendor running a commercial database, and that's what they have. It's a very complex CPU subsystem with their interconnect and lots of this. Okay, we try to beat or at least at par with this performance, but with this size, and leveraging our SQL chip as well as the techniques that we use to get rid of the need of this massive I/O subsystem. Okay, so that's what we're trying to do, and now how do we do it? Okay, so first let me briefly summarize what happens when you run a complex SQL statements, which it may be a join statement of 2 or 3 tables, but probably operating on several hundred million fact tables with dimension tables, or it could be over 1 billion. And, at the end of the day, once it's broken down into assembly instruction that the, say, x86 microprocessor can understand, which is a simple operation like add, subtract, multiply, shift, load, store, things like that, and then you iterate that over the loops of whatever, if it's a nested join that you're doing, and over the billions of tuples that you're operating, it can easily translate to 1 trillion assembly instruction. And even though that your CPU is running a multi-gigahertz, this still translates to many minutes, even hours. Okay, and then so one obvious thing that people try to do is, okay, let's deploy multiple processors, whether in in the same motherboard or multiple nodes through MPPs. You ended up with massive hardware build out. Just try to execute the query in parallel and partition the data, because you're just dealing with massive processing here, given you see that many number of instructions you have to execute. And then the next problem is the internal of these processor chips have on-chip caches. It's in the megabytes, a small number of megabytes in terms of size, but yet you're processing with hundreds of gigabytes of data in this query, and sometimes terabytes. So the on-chip caches, with the limited number of registers, even though the instruction flying really fast, is kind of useless. You pretty much go back and forth to memory all the time. And whether you're fetching for the next tuple or the next columns, it just doesn't fit in the on-chip caches. And sometimes if the memory is relatively small to the database size that you're dealing with, then you go back to the back-end storage. And now you're dealing with, in data warehousing, it's not a latency game, it's a bandwidth game. How fast you can get this data off the disk to the memory. Because, again, the CPU is operating out of a large amount of data, so you pay some overhead at the beginning with the latency, this latency. But once it's in the pipeline, it's the bandwidth that matters. Okay. So, so one thing I think that there's been a lot of talk in the previous sessions in this Percona conference as well as MySQL user conference is that what if we can get rid of this storage and just put everything in memory, either through flash memory or something bigger. You're still dealing with what I call the CPU bound problem, which is, as I mentioned, for data warehousing, your on-chip cache is just useless, doesn't fit. And so you ended up going back and forth to memory, and there's a lot of inefficiency in there in terms of making it fast for the complex query. So we take a different approach, and this is what I mean by new paradigm, is we invented SQL chip, which is the instruction is no longer those assembly instructions that has billions and trillions in it. Rather, it's just a set algebra instruction. This is something that is very obvious, probably you can say, that what are you doing? You're doing join? Well, why don't we have a join instruction here? You're doing aggregate? It's aggregate over what? Over a set, set of data, not one, register over another register and put in a different destination register. You're dealing with massive data that is flowing, but the operators are set algebra operators. So that's what we did and put it in the SQL chip. And then because it's hardware, automatically it is pipeline, inherently parallel, that means. And because there are multiple processing elements in here, again, it's not CPU cores in here, it's a direct transistor execution. You automatically get parallelization also from operating out of a different data set. And then our SQL chip operates directly out of our large centralized memory. And then the storage is very minimal in terms of the number of disks as well as the bandwidth that it requires. I'll go through the different architecture features that we put in to reverse that trend, that we don't need that massive I/O bandwidth like the traditional databases. Okay, so with that, let's go back to the I/O pain points. Again, in data warehouse application. So first is large data, and it's growing. We have a customer in the keynote speak that has about 300 gigabyte today, and is growing at 1 gigabyte a day. Mama source, that is. And this is just one of the many examples of MySQL users that are having pain points in their large and growing data. And from talking to several other customers, we also realized that sometimes the complex query is giving problem already at a few tens of gigabytes. It doesn't have to be in several hundred gigabyte or terabyte. Just by the nature of the complex query, it's already a problem. Second thing is how do you get in the data, the initial load, which can be several hundreds of gigabytes or terabytes, and need to be overloaded in reasonable amount of time, and usually during off-peak hours, that's overnight. And then you need to frequently update the database. It depends on your business model. Sometimes you need to pull, the most recent operational data out of your OLTP system into your data warehouse database or schema. And that's done usually through ETL, but more and more we're seeing that it needs to be done almost near real time, so frequently fresh. So, it's not just queries, so you need to have a good solution on that. And then, as I mentioned, complex query, sometimes we're seeing several hours, and in some of the TPCH queries, if you run against a vanilla MySQL, it just never come back after 2 days even. So that's how complex it is. And either it is because of CPU bound or because of IO bound, dealing with massive data. And our goal here is to provide solution data warehouse for the mass, and so we also need to deal with ad hoc online queries that are submitted by multiple users. So throughput is important also. And I'll mention an architecture later on in our database operating system that enables us to perform well on throughput-oriented workload. Okay, so what is the traditional way of solving the I/O bottleneck? And a typical solution today, they just keep throwing more hardware, just basically more disk spindles, because again, it's a bandwidth issue that we're dealing with, not latency or capacity. It's how do you get bandwidth? Each disk, if it gives you 50 megabytes per second, but you need in several hundred megabyte or even gigabyte per second speed, then you can just multiply the number of disks that you need to put in the hardware complex. So, to give you more examples, this is top performers in TPCH in 100 gigabyte workload, as well as the 300 gigabyte. And I'm showing here what people have done traditionally, trying to solve this performance by brute force and massive hardware build out. And you can see, anywhere from few tens to over 100 number of disks that you stripe in order to get the bandwidth. And you can see just to run 100 gigabyte, look at the capacity in the ratio of storage database that you're running with. This is just brute force way to solve I/O bandwidth. And our platform just have 8 standard SAS disks, 2.5 inch, and where we stripe it using RAID 5, so equivalent of 7 disk striping, and tiny in terms of the storage relative to the others, or the number of disks. And 300 is even more, 300 gigabyte. So that's what we try to reverse the trend, and again go in line with trying to be low cost and affordable for the masses in terms of providing data warehouse solution. So it's two things that are important in reversing this trend is that rather than keep adding I/O bandwidth, how do you reduce it? How do you minimize the I/O traffic? And second is that even if you have to have an I/O path in your query processing, how do you hide it? How do you overlap the I/O processing with the query processing? So some amount of prefetching, look ahead needs to be done on that. So the first thing, quite important, I think this is pretty obvious. Other companies that are deploying data warehouse solution, they use Columnstore database instead of RowStore. And to illustrate that a little bit, let me show you what happened here. in traditional row store, if you need to have a query that needing these 5 columns, call it C1 through C5, and because of the way the storage layout is done, you keep getting the other unnecessary columns also. You bring it to your buffer cache and you throw it away once it's in the, some of it that you throw away, but you ended up bringing, row by row, that you need. In this particular example, say you're doing some kind of filtering, and so some amount of table scan is needed. In a column store, you have the luxury of just bringing those 5 columns. So, so you see already is the amount of I/O that being generated by column store is already a lot smaller. Combine that with now you have the luxury of doing compression, because you're dealing with data of the same column. Usually there's some pattern in it. There's some range of the data that you can somehow squeeze the bits to store it. And so that's what we did. It's a compressed column store. Okay, so that's already a win. But that's not the only thing. So let me go back to the previous slide. Okay. So we talked about compression already. And one thing that important to mention here, some other database, like probably Sybase IQ, they do column store and they do compression, but before they can operate on the data, they have to uncompress it, and that's expensive. It'll lead to more delays, so we don't do that. We store and execute directly of the compressed data. So the footprint of the data layout in the disk and memory is identical. Next is we group and pool this memory, which is this one. Okay. So
why don't you take a couple minutes and just summarize that?
yes, yes. Okay. Apologize for that. Let me. I think this is one important thing, which is we have a database operating system layer because we have a custom hardware. You need to manage it, and just like Linux is managing general purpose hardware, we have our query processing module. So you need the intelligent storage management that understand, this column store. We have zero copy DMA because the QPM is connected through PCI Express. We have intelligent memory management. Our pages are or traditional buffer cache called block is not like 4 kilobyte or 8 kilobyte. Our smallest page is 64 megabyte. So you need to manage that differently, and they can go to gigabyte. Runtime scheduler, just like operating system, what we do is out of order scheduling. So quickly here, if you just do it serially based on the arrival of a query, then you ended up having idle resource cycles in the hardware. So we do out of order scheduling. So we prefetch ahead the I/O requests, and in whichever pages that are already in the QPM, we let the query go. So they are out of order, a query or task. Sometimes they are tasks within a query that we let it go first. And of course, is with data dependency still maintained, and you ended up packing more. And we have indexing, intelligent indexing. So sometimes you can afford table scan because of the indexes. And then I think on the TPCH, I'll make these slides available so you can read this. I apologize. But I think in summary, if I may conclude, what we envision at the birth of the company, providing high performance solution at affordable price. I think we've done that with our first product. So with that, thank you again. Thank you very much.